All right, y'all. Here we are at the end, coasting on through. Hopefully you feel like you're coasting at this point. That's the dream, is that you end any class feeling very, very confident that you can absolutely bomb the final and still get a good grade. That's to aim for, y'all. But no matter what, come Friday, every one of you will turn in a test and you will be done. That is always the mentality that I kind of try to have in classes. It was a great feeling. Once you turn in that paper, you're free. You've done everything you can, and it's a really nice, and that's true of all your classes. Once you turn in that test, hopefully that's the last thing that you have to do for that, and it's a great feeling.
You call this so it's Friday.
Huh?
It's Friday.
Yes.
Friday.
Yeah. What did I say different day?
Yeah, you say it.
Okay. No, I didn't know if I said different day. Yeah, Friday at 4. Friday at 4. Be here. I guarantee you there will be some non-zero amount of people that miss it. It'll be very sad for them. But not for you, because you'll be here and it'll be awesome. So, to that end, let's get going. I don't have too much, so we've kind of gone through. So last Wednesday, I did the overview for rotational stuff. And then Friday, I did the overview for what was on test 1. And so today, literally all I have to do is the overview for what was on test 2. All the 4 weeks ago or so. And that'll be it. So I'll do the same thing I did last time. I'll point out the one problem that tons of people missed. It was just one problem. Again, really, really happy with how this last test went. Y'all did great. I may look and see if there's 1 or 2 more just to kind of pad things out a little bit. 1 or 2 more, like the other 2 most missed ones. But again, last test went really good. I was really pleased with it. So last test was on, let me remember through my brain, momentum, conservation of momentum, conservation of energy, and then harmonic motion, harmonic oscillators, and universal gravity. And so the one question that most people missed was on, again, like before, it was those kind of topics tacked on to the ends, the one we didn't spend a ton of time on, because there wasn't too much to say, we just don't have a ton of time to spend on them. It was harmonic oscillators. And I've already mentioned this, but now it'll be in writing. So a harmonic, the motion of some object is given by the function x of t equals 7 cosine of 5t. What is the frequency of this object? So that was the question. Go ahead, see if y'all can figure it out. While you're doing that, again, I'll kind of rummage around and see what there's one more question I can maybe talk about a little bit. But again, y'all did really good. This is the only question that a majority of people miss. Yeah.
You want the natural frequency or the angular?
That's the key. Regular old frequency. And this is what threw people off. I want regular old frequency. And I should put the units here because I don't want to be a Neanderthal. Meters. Again, just looking up that one question. All right, so basically people picked between one of 2 answers. Some people said 5, and some people said the right answer. And those were not thereby showing you those aren't the same thing. So the reminder to you all is that anytime you have this harmonic thing going on, anytime you all have, so a cosine function, does this up and down and up and down and up and down and forever and ever and ever and ever and ever. And it has the form of the amplitude. So 7 here is the amplitude times cosine of omega t, where omega is the angular frequency, also known as the angular velocity. And so the key here is I wanted f, not omega. And so to that end, we had to remember that other way around, omega equals 2 pi f. So frequency is how many times it happens per second. Omega is how many radians per second. So the conversion is really simple. If you want to go from how many times per second to how many radians per second, you just multiply how many radians per something. So 2 pi f. That's on the formula sheet, so you don't need to have that memorized. So rearrange that, omega over 2 pi, and in this case, that 5 is the omega. So it ends up being 5 over 2 pi, which, isn't 5. It's something smaller than that. And it really doesn't matter what it is. It's a number. It's a number that's smaller than 5. And then the units for this, there's a variety of units. So, I don't know. Someone plug that in and tell me. What is that? Anyone got a calculator on hand? All right, we'll see who wins. Who's already got one on them?
7.85.
I think you did 5 divided by 2 and then multiplied it by pi. Yeah. But that's good. That's good. All right. Anyone else?
0.796.
All right. That'll do. Seconds inverse or hertz. Either one of those works. But that's a great point. Be very, very careful. If you plug this thing in as this written down, but you don't put the parentheses, it will give you the wrong answer. And who knows? Maybe I'd be mean on the test and put that as an answer. So that is it's good for those things to kind of pop out. Be really, really careful with that. And you can always check if your answer makes sense. Pi is just a number, 3.14. So I'm dividing 5 by about 6 something. So I should get a number less than 1. So that's how I was able to kind of check that in my head. I do not have the ability to divide by 2 pi in my head. But looking at this, I knew it would be some number less than 1. That's a good check. All right. Okay, the other problem that people did pretty decent, it was just a little bit over 50%, so you know what? We're not in a rush. I'll check it on here. An object, we use correct English. An object with a mass of 3 kilograms is tossed straight up with a velocity of 8 meters per second. If air resistance / friction does a total work of negative 20 joules during this time, how high will it go? If air resistance does a work of let's just keep it simple, does a total work. In this case, the work it does is from when it leaves my hand to the highest point. That's the part I'm specifying here. So this work here, if air resistance does a total work of negative 20 joules from when it leaves my hand to the highest point, how high will it go? See if you all can think of how you would set up this problem. You don't need to necessarily solve it. You can if you want to. I will solve through it as well. But this is a great tip for studying. When you look at a problem, do you immediately have an idea of how to solve it? If not, you should solve that problem. If you don't immediately have a sense of what to do here, you should start working through it. That's a great study skill for any class you ever have. If you look at this, you immediately know what type of problem this is and how to go about it. That means you could probably move on to a different one. You could be wrong, and if you're unsure, just do it. Just do the problem and find out. When I studied for things in my undergrad or grad classes, I didn't solve every single problem again from scratch. I just looked through and found the ones I didn't know how to do. And that's the ones I studied. Alright, so there's a couple key things that tell us what to do here. There's a couple key things that tell us what concepts we're going to use. We have an object starting low and ending high. We have a beginning and an end, and we have work. We have a beginning and an end, something changing height, and we have a work being done. And so when I see those things, that's an indication it's conservation of energy. If you see something changing its height and work being done, basically if you see work being done, you immediately should jump to, there's only a few things. Work equals FD and conservation of energy. Those are the only things that use work. Yeah, those are the only things that use work that I can think of right off the top of my head. So, let's think this through. What do we have? We have mass. We have initial velocity. We have work done by friction. We are solving for final height. I call it HF. You can call it YF, whatever you want to call it. Okay. So I'm going to tell you all, this is a conservation of energy problem. See if y'all can set it up before I write out the equation. Give you all a few moments. What is the conservation of energy going to look like with work involved? So there's a couple ways to write this. I'll write it both ways. It's the same thing, just written two different ways. On your equation sheet, you have the following. Work equals the change in energy, which is energy final minus energy initial. The work that's done on the system is how much energy you gain or lose. So remember, energy is conserved in the entire universe. So in this case, when I say gained or lost, it's lost to what's around it, the environment. Energy always goes somewhere. You can't destroy it, you can't create it, but you can move where it's located. Change the types of it. So that's one way of writing this. The other way is if I just move the EI over here, I get energy initial plus work equals energy final. Look, I just rearranged that equation. Like I didn't do anything fancy. Both of those, it's the same thing, just written two different ways. It's just a tiny bit of algebra. So then, we just take either one of these. I don't really care. I'm going to use the one from the formula sheet because it's in the formula sheet, so maybe a bit better. So negative 20, that's my work done. That's how much energy is lost in the system. It went to the air around it. There's no way you could actually account, that is something you just have to measure. Calculating the energy lost to the air around it would be an absolute nightmare. How would you calculate? You would measure it. In the real world, how do you measure friction, energy lost to friction? How do you measure energy lost to air resistance? You calculate it because you measure it. Because it's incredibly complex. It's incredibly complex, this kind of energy. Friction is okay. You can do friction. Mu mg, that's the force due to friction times the distance. But air resistance, oof. Let me just list all the variables involved in air resistance. The cross-sectional area matters. The density of the material that it's going through matters. The air, how dense is the air? There is then also something based on the shape of that object. So it's not just cross-sectional area, it's also the shape of it matters. Whether, it's conical or spherical or, an airplane, what the heck is that? That's a bunch of different things. Very complex. Very complex. So, anywho, just to let you know, it's complex. All right, great. So, what energy final do we have? At the highest point, we literally only have gravitational energy. At the top, it's not moving. There's no kinetic energy, there's no spring energy, there's no rotational energy. We're going to assume this ball is not spinning. That would introduce some fun complications. Minus, what energy do I start with? 1/2 mv initial squared. There is no we just say it wherever it starts, we set it 0. That's a good assumption to make. Set the starting point at 0. Technically, I didn't define, I say how high does it go. If it went from my hand, technically we'd have to say how high from what, how high from the hand, yada, yada, yada. Look, if it's not clarified, you have to make assumptions. If I gave all the specifics for every single problem, there's so many assumptions you have to make in problems. Anywho, at this point, y'all, it's really simple. In fact, I shouldn't be putting in numbers yet. Great, number 4, you put in numbers. So negative 20 equals, and it's just plug and chug. 3 times 9.8 times HF. 1/2 times 3 times 8 squared. And it's just an algebra problem. Whatever, you do some algebra, you get the answer. Woo. The setup is the hard part. Doing the math should always be the easy part for you all, at least in this class. When you get to statics, the math will be the hard part. Yay, system of equations. Setting it up may also be slightly tricky. But for physics, right now we're just giving you the foundational, so I'm not making the math a doozy. Alright, that's it. Alright, so cool, there's that. And then really all I have to do with this, the only other thing I want to mention is there's technically 3 free response problems. There was 3 free response problems. I'll quickly remind you all what those were, how to go about them, and we'll call it good. The reason I go over the free response is they are a good indication of what's important. I have to pick 3 types of problems for the free response. You best believe I'm picking ones that are important, that cover the concepts I need you to know. That's why I chose them. I actually spent, like all the problems in here, I have to put a good amount of thought into these things. All right, so test 1, free response. Let's see, number 1 varied for different people. But let's go with the one I remember first. The asteroid. An asteroid is traveling with a velocity vector of v equals 70 I minus 60 j. And then there was 2 parts. Part A. We had 2 options for destroying this asteroid. How fast, and actually we need to give you the mass, a 20 kilogram asteroid. How fast do I need to shoot a projectile, a 3 kilogram projectile, to stop this asteroid? Assume the projectile gets stuck in the asteroid. All right, that was the first one. And then the second one was, alternatively, we can blow up the asteroid. If one piece goes off with a velocity, if one piece is 12 kilograms and goes off with a velocity of v equals 30I minus 20j, what is the velocity of the other piece? All right, so spend a few moments, see if you remember how to solve this. What kind of problem is this? Again, last test was conservation of energy, conservation of momentum, universal gravity, and harmonic oscillators. So this will certainly fall into one of those categories. Which category does it land? All right, this conservation momentum. There is collisions, there is separations. It's conservation momentum, and then you have to just, you just got to set up conservation momentum. This first one is mass of the asteroid times its initial velocity equals
and then they get stuck together. Oh, oops. Plus mass of projectile times initial velocity of projectile equals the mass of the projectile plus the mass of the asteroid times its final velocity. If we want it to stop moving, that's going to be 0. You add up all the MVs equals, you add up all the MVs. Conservation momentum. Real straightforward kind of math here. MV plus MV, all the initials equals all the masses times the velocities at the end. Plug and chug, you get some numbers. Not too much to say there. This one here at the bottom, this is the exact opposite. This is I start together and I split up. So you get mass of asteroid times its initial velocity. To clarify, this is velocity A, velocity of the asteroid, equals, we get the mass of piece 1 times its final velocity. So that's the velocity final of object 1, plus mass 2 times its final velocity, and that's what we were solving for, was this. Something I gave you in the previous one was I gave you mass 2 in the one on the test. In this case, you just have to use a little bit of cleverness. If this is the mass of the asteroid, it's 20, and the mass 1 is 12, you can easily figure out that mass 2 is going to be 20 minus 12. There's 2 pieces. If one's 12, what's the other got to be so it gets to 20? 8. So there you go. Conservation momentum. Easy peasy. Conservation momentum is such a cool thing and how useful it is and how it literally applies to everything. Literally every interaction, conservation momentum works. Like me running into the air particles around me. Why do they move away from me? Because when I hit them, they're like hard spheres that are bouncing off of me. They're each moving on their own, and it gets super complex. But literally everything that interacts with each other, conservation momentum explains it. And it's so simple. MVs, add up MVs equals add up MVs. All right, so that was the first one. A lot of people chose this one. A lot of people did great on this one. Fairly formulaic, conservation momentum. Fairly straightforward. The next one that people largely chose, test tube free response, a spring with a spring constant of 50 newtons per meter launches a ball 3 meters high. I have no idea if I can make it that high. It'll work no matter what. Let's make it so it's definitely possible. 0.7 meters high. 2 parts. How much was the spring compressed if no air resistance? How much was the spring compressed if air did -5, let's make it really small, -2 joules of work? I need to give you the mass of the ball of a let's make it larger. 7 kilogram ball. All right. Same thing. What kind of problem is this? That's really the question. If you can look at this and have a sense of what problem it is very quickly, that's a great sign. If not, that's still fine. Spend a little bit more time. But again, that's how you know you're prepared for any test in any class you ever take, is to be able to give it some problem that you've seen previously in the class and say, yep, I know how to do that. Or one that looks similar to something you've been preparing for, anything like that. So you should be somewhat primed on how to do this one. It's conservation of energy. Something starts somewhere, ends somewhere higher, there's a height difference. Part B says stuff about work, so that immediately kind of triggers some things. So, what is part A going to be? There's no work done by anything. So this is just simply energy initial equals energy final. you decide. What is my energy initial? It's the energy stored in the spring, 1/2 kx squared, equals mgh final. There's at the highest point, that's the only type of energy it has. Really straightforward, plug in, solve for x. You have to realize x is the amount that a spring is compressed. A really common mistake people sometimes make with springs is they put the equation for the force of a spring, which is just kx. So energy in a spring is 1/2 kx squared. And I'll make that k actually look like a k. The force a spring exerts is just kx. So great, there's that one. The one down here is work equals energy. There's work, so, you know, same thing, but work plus energy initial equals energy final. It's the exact same equation with a -2 in front of this thing. So work due to air resistance, boom, there it is. There's the work due to air. Work due to air plus, so it's literally the same setup. Do you know where to put the work? Do you know whether it should be on the left side or the right side? Remember, the reason it's on the left side, it comes from this equation, but then it also, the energy final should be smaller than the energy initial because we lost energy. Air resistance takes away energy. So whatever this term is here for the energy in the spring, that will be larger than the final energy because we lost energy. How much did we lose? -2 joules. And again, I use the word lost. It got transferred to the environment. It left the system. You're going to hear that phrase a lot as you kind of go on. What is the system? What is the environment? The system is what you care about. The environment is everything outside of that. Energy can flow in and out of those two things. For example, your air conditioning unit, if you consider your house, your system, your air conditioning unit pulls cold air from the outside environment, which is a really weird idea. Or you can think of it, your air conditioning unit, when it's cooling your house, it's taking heat from in your house, it's taking energy from in your house and kicking it outside. If you're trying to heat your house with your air conditioning unit, depending on what type you have a heat pump, it pulls hot air from the outside, it pulls energy from the outside and brings it into your house. All your air conditioner does is move energy from inside to outside or outside to inside, depending on whether, if you're heating, it's bringing it in. If you're cooling, it's pumping it out. All heat is energy. Heat is a type of energy. If you want things hotter, add energy to it in a certain way. You want things colder, take energy out of it. That's all an air conditioning unit does in a clever way that you'll learn about maybe eventually. PV diagrams and all that. All right. Fairly straight. Again, a lot of people chose this one. And then the last one, which is probably the most important one for us to kind of go through because it's the one the least people picked, was the boat. Was the boat problem. And it was a little trickier. It's actually, I probably will change it in future generations. You know, most of these I'll tweak in some way. But this one in particular, I need to make some changes. So let me just give the big piece of it. A boat has a velocity vector given by v of t equals 3I plus 2j. And let's make this boat have some mass to it. 200 kilogram boat, fairly light boat, 800 or 400-ish pounds. All right. So then, wind blows the boat with a force given by F equals, and I'm going to make this way bigger. This is one of the problems with this one. Let's call it 300I minus 100J. If the wind is blowing the boat for 5 seconds, what is the final velocity of the boat? All right, so that's the main part I want to focus on. This is the part that's the most meaningful. Part B, I'm not going to worry about too much. Part B, I can kind of do a little bit more manipulating than this work we'll talk about. But this one, The concept here is very valuable. So see if you all can figure out what to do here. How do we approach this problem?
Are these numbers flipped with the exam?
Oh, they're all made. I just literally made them up.
Okay,
Yeah.
I think it was similar because the force was like 3 newtons.
Oh yeah, the problem I gave on the exam, the wind did almost nothing.
Yeah, I got scared because I got.
Yeah. Yeah, the numbers I gave on the exam for this one, the wind did almost nothing because I chose a really small force for the wind, like 5 and 3. And I, just didn't think it through when I made it. It's fine. The problem was totally solvable. But if you apply a 5 Newton force to something with a 200 kilogram mass, it's not going to move much. F equals ma. If you know the force, 5 divided by 200, the acceleration you get is minuscule. The acceleration you got was minuscule. So then what's cool about this problem is there's actually 2 ways to solve this. There's 2 ways to solve this. You can solve this using force and kinematics. So you can solve this remembering that F equals ma. So F, and actually, there's a reason you can solve it 2 ways. F equals ma, you can find the acceleration. And if you know the acceleration, you have velocity, you have acceleration, you have time. So if you find A equals F over m, it is a vector. So you got to do things in components. You got to find the x component, the y component. But then you can do v final x equals v initial x plus a xt. You can also do v final y equals v initial y plus a yt. That's one way. The other way is remembering, and this is the one I want you all to also, that's great. This is fantastic, totally works. What I also want you all to remember is that F times t equals the change in momentum. They end up mathematically being the exact same thing. So F times t equals the change in momentum, i.e. F times t equals m v final. Again, these are all vectors minus v initial. So you do have to do this in x and y. So fx times t, I'll write it out as unpleasant as it is, fxt equals m vfx minus vf naught, and then you have fyt equals m v final y minus v final initial. Now, if you kind of play around with these things, you will realize they're the same. These 2 equations, when you kind of do these problems, you end up doing the exact same math. You end up doing the exact same math. If you divide the mass over force divided by mass, oh my gosh, it's acceleration. Oh look, and there's a time times the acceleration. So again, this problem, either way you prove it, this is a good example. So Ft equals the change in momentum is literally from kinematics, from F equals ma and down here. It all connects, y'all. All of physics should, no matter how you solve it, if you're using the right concepts, if you do it 2 different ways, it should still work. That's one of the cool things with Physics 1, is there is sometimes more than one way to solve a problem. Physics 2, you're going to very often just have one way to solve that problem. Yeah.
How do you go to the second part with BFX minus BF?
Yeah, so momentum. Yeah, so the question was, how did I go from here to here? So momentum is mvf minus mv initial. The mass of the boat doesn't change, so I just pulled it out.
Okay, so would the second part be BF?
Oh, did I, yeah, that should be a y. Sorry. Boop, y, and that one should be x. I don't know why I put f's there. That's my problem. V initial x, V initial y. There we go, yeah. Final minus initial, yeah, thank you. All right, y'all, and yeah, I mean, that's largely it. One last thing I'll mention from this section, and it actually connects back to something I mentioned to you all last time. Remember, there's balloons in here. Oh, nice. Didn't even notice that. I want to remind you all about this problem here. Where is it at? It's actually from what I covered Friday. This one, up here. A car is going in a circular path with a radius of 10 meters. How fast can the car go if the friction is that? So remember I told you all the force going inwards is mv. If you add up all the forces going inwards, it equals mv squared over r. There is another type of this problem that is again, there's a roller coaster, there's that one. And the last example I want to mention to you all, this was not on the last test, so I'm just going to kind of chuck it here at the end. Remember, there is one last major example of something going in a circle, other than a roller coaster, other than a car going around a curved road. Yeah, the moon orbits the Earth with, I'm not going to put the moon because then I got to use real numbers. Some satellite orbits some planet orbits planet B with a velocity of 5,000 meters per second. If it orbits at a radius of big number 7e6 meters, what is the mass of the planet, of planet B? This is a really cool problem because it lets you determine the mass of planets just by watching something orbit around it. You don't even need to know the mass of the thing orbiting around it. So this is literally a technique that I assume they used. Pretty confident. This is a technique they used, this is one way to figure out the mass of the Earth. They know how fast the moon's orbiting around the Earth. They know how far away the moon is. And they can actually figure out the mass of Earth from this. They could also figure out the mass of like Jupiter and Saturn and literally every planet in the solar system by just measuring the velocity of something going around it and how far away it is from the planet. That's the only two variables you need, which is really cool. It's crazy. It's like, how does that work? So remember, let's just draw a sweet picture. There's the planet. Here's the little satellite. It is orbiting some distance r, so it is making a circular path around this thing. And it is experiencing some force. What is that force? Remember, the force that points toward anything that goes in a circle, if you sum up all the forces that point towards the center, it equals mv squared over r. So then the question is, what is the force that keeps the satellite going in a circle? And that is Fg. That is the only force acting on something orbiting a planet. It's just the force due to gravity. We're assuming there's definitely no air resistance out in space. So it is literally the only, and we'll assume no other planets are close by to affect it. So long story short, Fg equals mv squared over r, where m is the thing that's orbiting it. So Fg is g m1 m2 over the distance squared, r squared, equals mv squared over r. We get to cancel out the mass of the thing that's orbiting it. I'll just call it m2. The mass of the thing orbiting it, that's the mass of the satellite. So let's call this guy m2. We get to cancel out one of these r's. And if you rearrange this equation, m1 equals v squared times r divided by g. And that's it. I just rearranged that equation. And g is a gravitational constant. I think it's 6.674 times 10 to the minus 11, but I'm going to fact check myself because I haven't used it in a little while. So I don't want to tell you all lies. It's on the formula sheet. Gravitational constant. Yep, there's my search history because I've looked it up so many times. Oh, so close. No, what? Depends where you look. Nope, 6.674. I did good. All right, 6.674 to 10 minus 11, that's G. And that's it, y'all. And you can find the mass of any planet. It's wild. You just need to know how fast it's going and how far away it is, and boom, this works. This is not, and you don't even need to make any assumptions here. Like, I guess the only thing that's important is that the thing that's orbiting it is much smaller than the thing it's orbiting, because then it gets a little funky due to where the center of mass is and all that. But a satellite is so much tinier than it that, yeah, this works. This is what they did to measure the mass of a bunch of different planets out there. They sent a little satellite around it, did this. It's cool. Super, super cool. But also they didn't need to send a satellite. There's plenty of moons orbiting planets. They could use those, assuming they're small enough. Assuming their orbit is circular, which most are. So, you know, there's slight electricalness to it. So, yeah, cool stuff, y'all. All right. That's it, y'all. I mean, you know, I could do more things, but at this point, you know, I'll just kind of hang around. If you've got individual questions, come on down. But we did it. It's the last class, y'all. Feels good. Enjoy. Good luck with studying, y'all. Great work. One way or the other, you made it to the end. And when you turn your test, you are done. What a feeling it'll be. Good or bad, you'll be done. You've done what you can. See y'all Friday.